Now, it may add stress and anxiety. If you have those things based on what I do, come to me and talk to me, and we'll straighten it out so that you understand there's supposed to be a little bit of stress and anxiety. But if it's unmanageable, you come to me, and when we work out how we can help you get to a place where it's not that. Right? Any question on that? Okay, so I'm not going to be the person that lays it out for you perfectly, but we only have 4 things. We have home.
Yeah.
We have homework. Right? And my style is, you don't have to do it until I give it to you. Right? Regardless of what it says, unless I hand you the homework, it's not assigned. All right? Whatever it says on Canvas, that's just bookkeeping. It's not real. What's real is when I hand you a homework, you do it. So homework 1 I've given to you. So homework 1 is assigned. Now the due date is to get you to do the work, right? Most people like a due date. And if you finish it before the due date, you get the bell or the applause or something. I don't know what you get.
It's different every time.
It's different every time. But if you don't do it, then you get the, it's late. But it's not late, right? It has to be done. So we have homework, we have reading quizzes. Reading quizzes are the same way. If I don't give you the reading quiz, it's not due regardless of what it says, right? I hand out a reading quiz in class, now the clock starts, right? Okay. These are 5 points. These are variable around 10 to 15 points, right? The third thing we have is in-class quizzes. And I call them NICE, novel in-class exercises. And those are 5 points. And those occur often every other day, every day, sometimes 2 a week, sometimes 1 a week, sometimes none in a week. All right? It's variable. So this is variable. You also get class time to work on these, and then they're due by midnight. So if you don't finish it in the time that I give you in class to do, you can finish it that night. And then even again, that's if you want the bell or the whistle or the applause or whatever it is, a little heart. But it's still acceptable late, and there's no penalty until I decide there is one. But basically, just get the work done, right? Now, this is what we have to do. Right? Oh yeah, the last thing is tests. And if you need accommodation for those tests, be sure to do that up front so that I have the knowledge so that we can get you to LAP and you can get what you need. If you need a note taker, if you need anything like that, I love LAP, right? Because in my book, I don't care how you get to the next level. I just want you to get there. I want you to finish this class, confused or not, stressed out or not, right? Whatever tools help you get to the finish line, I'm all in favor of those. Oh, gotta stay back here so I'm on camera. Hi. So the whole thing is, it's all about you, but you can't tell me how to do what I do to get you to the next level because I've been to the next level. I've been over the top of the mountain, as Moses would say. And when I came down, I got some fruit, and I want to share that fruit with you, but most of it's very confusing. And there's a lot of things going on. You carry a lot of stuff with you. You carry work and school and family and blah, 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 and COVID now, right? So, yeah, this adds to all that, but the reward is huge. And getting your mind to accept lack of control and get used to that makes it much easier, right? The expectation here is that you show up and you do your best, and that's it, right? These are our 4 things. So don't lose track of that. That's how we do the measuring. But again, all of it comes to you from me. Then you turn it back in on the internet. Yeah? Questions? Okay. So we cleared that up, I guess.
And I'm assuming that's for last year portion because the lab is a whole other beast.
Oh, right.
I'm Rebecca. Some of you remember me from last semester. I am one of the tutors here on campus. I'm a drop-in tutor here at Lompoc Valley Center. I'm also working this semester as a lead/mentor tutor, so I am working with all of them. I put up here a schedule of your drop-in tutors. There is also scheduled tutoring, which you would contact the tutorial center to set up. And there's also the STEM Mesa Center, which is a great resource, and they have tons of great tutors over there. But I put these up here just for your own reference, for the times that we're available, just to stop in, get help, whatever it might be, for any of your Chem 150 needs. And a lot of us do several topics, so there's other classes. There is a full schedule listed on the tutorial website as well. But this is just for you guys, because I know this is a hard class. I just took it last semester. So good luck for everybody, and I hope to see some of you if you need me, okay? And he's great, I promise, I have him. Have a good class.
Can I ask you a question?
Oh yeah, no, go ahead.
You're
I
here.
put LBC and I'm Rebecca.
Yes, but you're here in LBC. Do you do any Zoom for people
Yes,
that live
sorry, I
far
did
away?
not mention that. We are also available through Zoom. We have been figuring out how to get the Zoom links available to you. We had a little trouble last semester, but I believe if you go on to the website, it'll either have our link or you can talk to the people in chat and they'll give you our link.
Okay, cool.
To access us, and we're all available through Zoom, so you should be able to contact any of us, and that's the same for scheduled tutoring as well. So if you want to meet for a scheduled session, which should be an hour or possibly more depending on your needs if you're LAP, you would be able to set all that up through the center, and you get to choose if you want to do in-person or Zoom as well. Okay.
Question.
Any others?
So to contact you and set things up, would that be through like the Cranium Cafe link on the page, or would we go through the page to find the drop-in tutoring?
So if you go onto the Hancock webpage, they have under Student Services, the Tutorial Center.
Okay.
On there, you'll see the drop-in list, and you'll see the list of all subjects. You would go on there, and it actually has a page that walks you through the process of applying, or not applying, but receiving tutoring. And it's all free. Like, it's completely free. It's one of the benefits you have here on campus. Any other questions? Did I answer your question? Okay. No? All right, well, this is for drop-in tutoring. Again, there is also scheduled tutoring available for you, and I would also recommend the STEM Center. There's the new STEM Center on Santa Maria campus, and they have a ton of great tutors as well. Okay?
Thank you.
Bye, guys. Thank you for letting me speak.
Get a picture of that if you want it. You have another alternative, that is yours truly. I'll walk you through any problem, anytime that I'm here, or anytime you contact me on Zoom. I'm glad to do it. I enjoy it. It's what I do with my free time. And this year, since I'm going to SBCC and doing an organic class, I don't have the time on off days that I used to have. But even on Monday and Wednesday nights, I'll be glad to do it. And if I'm available during lab down there while I'm watching those guys do their organic thing, then I'll even help you then. So I've been known to check my email anytime, day or night. So take advantage of that if you want to. Okay. Now about chemistry again. We remember what are three types of things we have? Because this is going to be our in-class quiz, I guess. What are three? We have atoms, molecules, compounds. Now, one of the questions we ask as human beings is, can we just throw any random stuff together? So can we just make this chemical, sponge? So this is what you study in organic chemistry: sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen. Does anyone have their laptop with them?
Yes.
Do a Google search for sponge. Anybody that wants to. Or S-P-O-N-C-H.
Is it gonna be the?
All caps?
Yeah, all caps.
Fruitcake.
Well,
Marshmallow cookie coconut discovered. Okay.
Okay, that could be, but that's probably not,
Should I preface with chemistry?
Oh, yeah.
could be, or chemical.
Oh, some sort of cake.
So look how smart those people are, right? They named their cake after the elements in organic chemistry. So it didn't come up, right? It wasn't the first thing that came up.
No.
And so go ahead.
SPOT is the acronym for sulfur, phosphorus, oxygen, nitrogen, carbon, and hydrogen, which account for the main elements which are found in every single living organism in the universe.
Wow, so I said something and we looked it up on Google, it's true. So everything on the internet's now true. Okay, but my point is, we put together elements to make compounds, all right? There are rules that are associated with that. You may find a compound with all of these in it, but it won't be 1 to 1 to 1 to 1 to 1. If we start looking at how we put it together, that's why we ask all these questions. That's where all the base knowledge comes from, is how do we account for the compounds that we see? How do atoms go together? How do molecules form? What are the forces in between them? And that's why we do this, right? That's the thinking part of it that I love, is not the rules, but what we make out of the observations. And that's all this really is. Nobody knew any of this before they started watching how they put it together. So when we move forward in a serious pursuit of chemistry, what we're doing is we're looking at observations that other people made that gave us generalizations that we can use. Trends. And that's what it's about. It's about the trends. And anytime you go to a university, that's what people are looking at, the trends. When you break off and do a new research project, it's based on the trends that came from before, the knowledge that came from before. And you start breaking it down into parts that we can understand. The first thing we do is build a base knowledge of it so that we can understand things. And again, this isn't in the book. So if you're thinking I'm going to go by the book, I'm not. Because why? Because the book you can read. You're in college. You can read. I know you can read. But what you can't do is know from the experiences that I have that make it good for me to be a teacher, even if my teaching is flawed, right? I'm standing up in front of you sharing what I learned from going farther in a small direction continuously for years and years and years, spending time in a lab, doing things nobody else wanted to do for very little money and very little recognition. But I did get 12 papers. So if I get papers out of it, that means it's got some scientific merit that somebody thought, hey, that's good enough to publish. All right? So when I come back to teaching without having it laid out in a perfect order, it's because I didn't get there in a perfect order. I didn't get there from a book. I got there from observations. So I don't know why I'm being so defensive today, but I am. And I appreciate you guys being here, and I think this is the kind of experience that you're supposed to have in college, which is, man, you can do this, but you're gonna be doubting. You're gonna be doubting it, right? And now I'm off chemistry again. Okay. But I got my slideshow, so any questions before we get going? Dead silence. All right. That's fair enough. Okay, so I want to start off with the slide and see if there's any questions about this. Okay, so we have these things called polyatomic ions. All right. And without any kind of background or anything, does anybody know what a polyatomic ion is?
Poly means 3, right? Or
Many.
Many. So
Many ions.
Yeah,
Right. Many atom ions. Okay. So what do we know what an ion is yet? Exactly. Go ahead, Jules.
It's when an atom in an element is either has too many electrons or not enough electrons, so it has a charge on it?
Correct, right? So we have a difference in the amount of electrons and the amount of protons. That's all an ion is. Now, if you put a bunch of atoms together, is it me or is it memorized? Put a bunch of atoms together and you don't have the right number of electrons to balance out the number of protons associated with the multiple atoms, you're going to get a charge. So for example, nitrogen, when we look at the periodic table, which you either may know or not, the reason I'm asking this is because I want to see where you guys are. The people that have my class before hopefully know this. Nitrogen has 5 what we call valence electrons. Okay? Hydrogen has 1. So if you make this molecule, there should be 9 electrons. But it has a +1. So instead of 9, it has 8. Okay? And that ion is called ammonium. Then we have hydronium, H3O+, which means we have less electrons than we should. Hydrogen has 1, so there are 3 hydrogens, so you should have 3 electrons. Oxygen has 6, so again, you should have 9 total. But you don't because there's a plus, so you only have 8 electrons. Each electron has a negative charge that's balanced out by a proton, right? Okay, so hydronium and ammonium, that's 2. I said 25 in the reading quiz, but it's really only 24. It's really only 23 in the book. So those were cation meows, all right? Those are positively charged ions. Anions, you have acetate, or written this way, same thing, still acetate, right? It's the ion of acetic acid. CH3COO-. It's called acetate. The best way to do this is to make some flashcards. You need to be super familiar with these, although likely I'll still give them to you. Cyanide. Again, carbon has 4. Do you guys have your periodic tables? And this is stuff that, it's basic, but we still gotta make sure we can do it. So can someone tell me how many electrons this should have? Based on valences, if anybody remembers valences. No. How many valence electrons does carbon have, and how do we know it has that many? No. That would be total number.
Oh, yeah.
Right? So you guys are close, right? You guys are giving me the total number of electrons. But we're only talking about valence electrons. What are valence electrons? Valence electrons are the electrons on the outside shell that can possibly react. Right? And if we look at our periodic table, there's a way of doing that. Does anyone remember that way?
I don't know the names, I know.
Oh? What is, tell me something about it then.
Go with it.
What it looks like.
Wait, hold on, I was looking over here, so what is it you want?
I want to know how many valence electrons carbon has.
Oh, you do the little like, hatchet.
Okay, so
And then you count.
you mean a Lewis dot. You count, but how do you count how many valence electrons there are? Where do we get that? Right, but where? How do we know? We can just look at the periodic table and know.
It's like the periods, right?
The number.
Yeah,
Number at the top or
yeah, there you go, Vincent. Right, it's the number at the top. It tells us. So column 1, 1 valence electron. Column 2, 2 valence electrons. This column over here, how many? 3, 4, 5, 6, 7, 8. Right? Are we? Alex, you got this? All right. And then in between, we have 2 plus whatever this is, right? Because those 2 come off, and then we have d orbitals right here. All right. So where did I steal this? Yeah. All right. So we're going to talk about periodic table and all this stuff again, but just the preview of what's coming is that we need to know these. So this is how many? What column is it in?
It's in column 3.
4, very good. And then nitrogen right next to it is,
5.
so then the total is 9. But, look, we got one more electron we gotta count for. So, 10. Okay, good. So cyanide has 10. Now, let's go down and do another one. Oxygen, hydrogen, hydroxide. Very common. Use it to form water. It's what ionizes water. H plus, OH minus. So OH minus. How many valence electrons in oxygen?
8. Oh, wait.
Total?
6.
6, right? And then 1 hydrogen, 7, and then
8.
8. All right. So get used to saying them, and like that's what I would do. I mean, that's how I got them years and years and years ago, back when the Stone Age, when I was your age. I would just say acetate, CH3COO. And it's memorization, it's boring. But you know what? All the classes that build on this class, they all do the same thing, right? You go to be at physiology, you have to memorize all the muscles, all the blood vessels and anatomy and all that stuff, right? You have to memorize the processes. These are easy processes compared to that. We have a table that you can look at. We don't make you memorize, right? So, next, we have the chloride series, right? Chlorine and oxygen. How many in chlorine? How many electrons in chlorine? 7. Okay, and oxygen?
Oxygen is 6.
So 7, 6 plus 1. All right. If we draw a Lewis dot, which you're not responsible for, don't get carried away. This isn't a part of the homework, right? This is just me discussing what we're memorizing and why, right? So what we have here in a Lewis dot structure, right, which we'll get to later in the semester, but here we are, we're starting off, right? We have 7 electrons. 1, 2, 3, 4, 5, 6, 7. And oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. So we have 2, 4, 6, 8, 10, 12, 13. But there's a minus sign, right? There's a rogue electron.
Then you make brackets, right?
Ooh, very good. You do make brackets. And you add that electron, and now it's a minus because it has one more electron than it should. That's what makes it an ion. It's polyatomic because it has 2 different elements attached to it, right? And we can use these anions to make things, and that's what we do, right? And they can be huge, right? If you're taking a psychiatric drug, like I should be, you probably have a huge anion, right? And then you put like lithium right here. And then lithium delivers it, and then you get the lithium for your brain, and you also get this giant anion floating around in there that bonds in a specific place to make your dopamine behave itself. So you don't get too excited. You can override that with caffeine anytime you want. Chloride. So we have hypochlorite. So if you look at these, there are 4 of them. Chloride, chloride, chlorate, chlorate. So the least amount of O's, hypo. Then you take away the prefix, then you change the prefix when you get to 3, and then you add the prefix back on when you get to 4. So we have hypochlorite, ClO, ClO2 chloride, ClO3 minus chlorate, ClO4 minus perchlorate. Okay, so now we're at 9. And you're going to forget ones. That's not the big deal. The big deal is you get used to recognize them back and forth so that you don't waste brain cells trying to remember what that is when you should be trying to make a compound. Next. Then we have the nitrate series, NO2 minus, NO3. Now we do something a little different here with permanganate because this is a transition metal with an oxygen. All right? But it forms a complex that can add or subtract to other things because the thing about transition metals is they can give up various numbers of electrons. So that's good. It's another one to know, MnO4. And the bonding's different, right? What is different about NO3 and MnO4? Why do I say the bonding is different? Where's manganese, Mn, where is it? On your periodic table, where is it?
Isn't it a transition metal?
There you go. That away, Nathan. So it's a transition metal. What about nitrogen?
Nitrogen is in non-metal.
Non-metal. Oxygen. Right. So if we look at nitrogen and oxygen, we have two nonmetals bonding. Here we have a metal and a non-metal bonding. So two nonmetals bonding, they're covalently bound. So these anions are covalently bound, but when they form a complex with a metal, they're ionically bound. This is ionically bound. And where's the charge on this one? But it has a charge. And it's -1. So anyway, permanganate. Then we have carbonate, CO3, 2. So this is two nonmetals again, right? So this is another way to look at these. So we have covalently bound nonmetals that share electrons and then have extra electrons with them. And then when they bond to a metal, they form an ionic complex. So we have carbonate, hydrogen carbonate, chromate, and dichromate. Right? Again, transition metal with a nonmetal forming ionic bonds inside a polyatomic ion. Right? But that's not what we need to know for these. We just need to be able to recognize both. Right? Chromate is CrO4 2-, dichromate is Cr2O7 2-. And you just expected to know that for some reason. It's a tradition that goes back hundreds of years, I'm sure. Oxide. So a lot of times you see an oxygen attached in a molecule, and you're gonna wanna say, wow, it's O2, so it's peroxide, but it's not. If it's O2 and it has a 4- charge, it's not peroxide. And how can you tell if it's peroxide at O2? Because the charge of whatever it's bound to, right? You're gonna be able to tell if it's +4 or +2. Then phosphate, hydrogen phosphate. Oh, I didn't do the whole, maybe that's missing. Wait, peroxide twice.
Yeah.
Well, now we're down to 23. Nice. Never noticed that before. We'll get rid of that. That's not good. And where's phosphite?
Would hydrogen peroxide be on there?
Ooh. No. Sulfate, hydrogen sulfide, hydrogen sulfate. Yep, that's what's missing. Phosphite. Let me get there. So 20. I need to move this. I need to make this one 20. Anyway, I can do that on my own time, but I'm going to put it down here anyway. Insert. Come on. Oh boy. All right. That's not quite what I wanted to get. Let's see if I get to that before I do this again. All right. So these are the polyatomic ions that we need to know. Right? And just keep working with them. You don't have to know them today. There's not going to be a test on them. But when the test comes, there may be a use for these. All right? So we need to be aware of them. And now we just covered all kinds of things that have to do with what we're doing this semester, which is we're expecting to know this is all covalently bound. This is covalently bound. This is covalently bound. That most of the polyatomic ions are between nonmetals. And there's only 3 that we have to know that aren't, which is permanganate, MnO4. And then what else do we have? We have, where's the chromates? Doggone it. They hit on me. There they are. Chromate and dichromate. So just 3 that are ionic polyatomic anions. Now, any question on what we need to know about these and how to recognize them? So what you really need to know is the charges, because that's how they go together, right? How many of these do we need? How many units? If you look at each one of these, you're looking at a unit. How do we save those units? We had tie them together with something of equal charge that's from the periodic table. And so usually it's a net. But you can string multiple polyatomic ions together on a metal if you can support them. So today. Oh, we didn't finish last time. Oh, that's the one I just did. Okay, and this memorize stuff, I don't mean memorize. I really mean recognize, right? Because you have the periodic table, so you don't have to memorize, you just have to know where these are, right? When I mean memorize, I mean know where they are on the periodic table, right? Know how to find aluminum. Don't be going, okay, I'll find aluminum on the test because I know it's on the periodic table. No, these are the ones we're going to use, so know where their location is, and it saves you time. And then if you save enough time, you can spend the whole test just thinking about the questions instead of how to do the question. So that's what that list is for. It's not to memorize, to have those elements committed to your memory. It's to be able to recognize them immediately and go to them on the periodic table. Like I go to carbon. Carbon is element, I don't know, 6. Yeah, and then fluorine is 10? No, 9? Yeah. And then hydrogen's 1, and then iodine's somewhere down on the right, low in the halogens, right? I know it's in the halogen column, which is the 7th column, right? And then oxygen, it's on the top, and then phosphorus is right in there, and so is sulfur, and then aluminum's like, oh, it's up across on the top. See, that's what I mean, know where to look. It's because if you start scanning under pressure, right, all of a sudden the periodic table becomes useless because everything looks the same. But if you already know, oh, I just go to aluminum. Oh, I just go to, so that's what this is. That's potassium is another one, right? First column. Lithium, first column. Silicon, where's silicon? And that's the practice, right? Where's silicon? It's right under carbon, right? Isn't it?
Yeah, 14.
All right, sodium's another one in the first column. Tin's one of those ones. Tin and lead are kind of in a weird place because you think they'd be transition metals, but they're kind of right next to transition metals, and they can have 2 types of charges. See, this is what's great about, oh, I didn't start that right. Here we go. Let's make it more, and there we go. Now we're talking. All right. And that's where we left off right there, right?
No, keep going.
Oh.
Going.
All right, well, that's why that is.
Going.
Oh, we did this.
Yeah.
Nice.
Keep going.
Whoa.
Keep going.
Oh, yeah, I remember this. And we did this.
I think we stopped at the water boiling. Right there, stuff. One more. I think we stopped here.
No, we had like a, remember you showed like the diffusion and osmosis, I don't know. Yeah.
Electrolysis. Right. So what do you guys usually think of electrolysis for? I mean, maybe not.
Separating.
Deionized water.
Yeah, deionized water.
I think it was hair removal.
Oh. What?
Sure, it's called electrolysis.
Like Nair?
I don't, no, Nair's not electrolysis. Anyway, So, yeah, so you do water and you separate it in hydrogen and oxygen using electricity. Yeah. And so, right now, the huge deal is to use water. There's these hydrogen companies, right? And what they want to do is use existing water to create a battery to drive cars. And the funding is huge right now. So that process is still not completely nailed down, but the money's there. Okay, so if anybody ever contacts you and say, hey, you want to come work on a hydrogen thing, you immediately say yes. Immediately. Back when they were starting in like 2001 or 2, I got a call from a company doing it, and it was allegedly an interview, but the questions they were asking me were more of what will you tell us for nothing kind of thing. And at the time, I just told them everything because I didn't even understand what they were. I just thought I was interviewing for a job. Anyway, so hydrogen bonds are broken, oxygen bonds are broken, so that's a chemical example. Remember, in the water boiling, what we're trying to do is we're trying to go, is it a physical change or a chemical change? If you change state, right, if you go from liquid to gas or gas to liquid or solid to liquid, then or just solid directly to gas, you're only changing state, which is a physical change, not a chemical change. If you're breaking bonds, as in electrolysis of water, you are doing a chemical change because a chemical change is breaking bonds. Distillation, right? Separation of materials of liquid, right? You have two liquids mixed together. Like, I just did this last night with a bunch of organic kids, right? We put sugar together with yeast in a pot and then left it under light in a sealed container, right, for 2 weeks to let the yeast and the sugar mix, and we made ethanol, right? So if you're ever busted and broke and really like to drink, you can mix sugar and yeast, put it in a container, seal that container, wait a couple of weeks, and then you have this ethanol sugary yeast thing, but the ethanol's still in it. Yeah, Don.
15 gallons of water, 8 pounds of sugar.
Anyway, so you could do that theoretically. You can't sell it, right? That's the problem. It's not that you can't make
You
liquor,
can trade with
but you
it.
can't sell liquor, right, without a stamp. So anyway, you make this mixture and there's water in it and there's ethanol, but you want to get the ethanol away from the water. And what happens is we use the physical properties of the two. The boiling point of ethanol is lower than the boiling point of water. So we put it in a special kind of flask, and the ethanol boils first. And it collects here at a certain temperature and then goes all the way down, and you collect it here. And then when the temperature gets up to 100 degrees, which is the boiling point of water, now all of a sudden you're just getting water and you're done with that collection. And you can get up to about 85% alcohol. In terms of proof, that's twice, right? So 85% twice is 170. So you could get 170 proof out of that method. But it's just ethanol, right? It has no flavor. So,
It's good vodka.
yeah. Again, that's beyond the scope of this class, but the thing is you can do it. So you can take advantage of physical properties to do a separation. Then there's filtration. If you have a liquid and a solid, you want to separate it, you just pour it through. So before we did the distillation, we had to do a filtration because there was yeast particles left over, maybe some sugar left over, maybe part of it didn't react. You want to separate that from your liquid so that you're only boiling the liquid because that is cleaner. So you do a filtration so you can separate liquids from solids that way. Chromatography. So when you have chromatography, what you're doing is you have two liquids. They can be similar liquids. For example, what does polar mean? What is a polar compound? Dom, go.
Yeah, I forget the term. The ions, they stay to one side. They favor one side over the other.
Well, that's pretty close.
I-
So the charge, if there's a charge involved,
Yeah.
one of the compounds favors that. So
Yeah.
there's a charged species, right? Do we remember the phrase, what does like dissolves like mean?
What does like dissolve like, would you?
Yeah, what does like dissolve like mean? No? Jules?
Polar, like, two things that are polar can dissolve in one another, and two things that are not polar can dissolve in one another.
Perfect. So if you have a charged species or a polar molecule, and all that means is that the relationship between the atoms isn't even, right? It's like, if I pull like this evenly from both sides, it just stays right here. If I pull harder on this side, it goes that way. If I pull harder on that side, it goes that way. If I'm pulling just like this, it's nonpolar. If I'm pulling this way, or I'm pulling that way, it's polar. So what I'm saying is, if it's polar, if two things are polar, they dissolve each other. If two things are nonpolar, they dissolve each other. But generally, a nonpolar doesn't dissolve a polar, okay? So chromatography says, if you have two substances that are polar, they're not exactly the same polar. So if you run them through a column, they'll travel at different rates. And that's all chromatography is, right? It's just taking advantage of the polarity of one solution versus the polarity of another. And if they're in the same thing, you can separate them by running them through long columns. In the old days, even in, not even that old, but a while back, the Earth wasn't young anymore, but it wasn't as old as it is today. And then you had a column and it was about this long. And your organic separations, you'd run it through this column, and you'd run it through like 6 different columns to get enough separation to separate your column. And that would be what you did all day long, right? So we used to laugh, small molecule chemists in inorganic, we laugh at the organic chemists because they spent all day doing a separation, right? And we separated in air sensitive ways in seconds. So anyway, but that's why it takes longer to get an organic PhD, because not only do you have to do all the chemistry that you have to do anyway, but you have to do all the separations along the way, and you have these big columns. It's a lot faster now. But does that make sense? Do you see how you have this solvent that dissolves your solutions, and then as it travels down this column, one travels faster than the other, and so you get separation. Okay, and that's basically the idea. And we went over this. Scale removal is another thing where you have calcium carbonate built up on a glass in your shower, and you need to remove that. So you use a lime away or something, and you can take that scale off. And then refining is you have crude oil, and you run it through a bunch of batch processes and separate the different components and burn them, right? And then that gives you the pure oil and gas that you use. Okay. Now that we've figured out that part, we have to measure things, and that's what we're going to do today in lab, is more measurements, just like we did for the first time. But this is a little bit more scientific, I think, if you've done the pre-lab. So length, meter, mass, kilogram, time, second, temperature, Kelvin. What we want you to know here is the different units, and make sure that when you're writing down a number, you recognize if it's a meter, it's a length. If you write down a gram, it's a mass. If you write down a second, you're using time. If you write down Kelvin, it's a measurement of temperature. So if you keep your units straight, if nothing else, you're going to get credit for trying to solve that problem that involves those variables. If you just put down like 7, it could be any of these. Right? It could be 7 moles, it could be 7 amps, it could be 7 Kelvin, 7 seconds. So there's no way to really know where that number goes. And if you're doing it in your head, that's great. But you're not doing it in your head for you, you're doing it in your head for me. And I don't know what's in your head. And you don't know what's in mine, thank God. And then, so Kelvin is a temperature. So if you have anything in Kelvin, you want to write K. If you have anything in time, you want to write S, mass, kilograms. We don't really use electric current that much. There's a little small portion where we do in lab. Moles, we do use moles. So we need to be aware of that. And I don't know if I've ever even used a problem with intensity, but luminous intensity is good for, it used to be called candle power, and then it was lights, and now we use lumens, right? They changed it to lumens. It used to be a 60-watt bulb, now it's however many lumens based on representing a 60-watt bulb. It's a very, very bizarre way of measuring. But the more lumens, the better, if you want to be able to see. So those are the ones we mostly use, and moles, right? And just things to kind of remember to keep your mind straight. A meter is about a yard, so 39 inches compared to 36 inches. A kilogram is about 2 pounds. A centimeter, 1 inch is about 2.5 centimeters. Again, you don't have to memorize that, but the more familiar you are with these terms, the easier it is to do the problems, the quantitative problems. So, again, chemistry uses big numbers and really small numbers, like millimoles, like milligrams, and really big numbers like kilograms, right? And how do we handle them? And that's scientific notation and numerical scale. So if you struggled with this last time, guess what? It's back. Scientific notation and numerical scale. So we have the atomic scales, femto, 10 to the minus 15. It's tiny, right? Pico, 10 to the minus 12, and then nano, 10 to the minus 9. We're all used to hearing nano now, right? Nanotechnology, nano, the little Apple thing. But anyway, 10 to the minus 9, it's a very small number, right? It's 0.000000000, I think that's enough, 1. I think that was 8 and a 1, right? And then what does it say here? It says 4 times 10 to the minus 9. There it is. 1, 2, 3, 4, 5, 6, 7, 8, 9. So each nanogram represents 8 zeros and then that number. That's a very small thing to measure. Our eyes don't work on that frequency, right? We can't look at something and go, oh, yeah, it's about 2 nanograms, right? But our color perception can, right? We can differentiate in blocks, right? Between 450 and 700. And then the common scales, micro, milli, centi, deci, kilo, mega, giga, tera. You don't have to memorize those, but again, the more familiar you are with micros 10 to the minus 6, the less you have to make it appear that, the less time you have to spend identifying it. And that's where the outside of class time comes in, right? Don't memorize the table, but every time you do a problem, think about the units. Say the units in your head while you're solving the problem. Oh, that's 18 microliters. That's 18 millimeters. That's 14 centimeters. That's 10 deciliters. That's 1 kilometer. And then you just start remembering those names, those phrases, and it'll help you when you go to look at the conversion factor cheat sheet. Instead of panicking because you don't remember what a microliter is and then looking and going, I can't find microliters on the sheet. Right? That's what I'm talking about minimizing your anxiety. The preparation calms you down, right? You don't have to memorize. You only have to recognize. Right? The important part is, how can you explain what's happening? You don't have to be able to. You're going to try to, right? These are the accepted rules that we have. Doesn't mean they're right? Doesn't mean there aren't layers upon layers of nuances to each and every one of these ideas we're sharing. This is the introductory way of explaining the universe in a chemical way. Right. Scientific notation. N times 10 to the n, where n is 1 to 10, basically, and the little n is an integer or an exponent. So some practice, and hopefully I have these, I don't remember. What is 0.00000412 in scientific notation? Right? So what we're going to do Oh, I have that little cute little arrow thing. I go 1 day without presenting and I don't remember what I'm supposed to be doing. All right. Laser pointer. So we're gonna move the decimal from here to right there. So we're gonna go 1, 2, 3, 4, 5. So that's 4.12 times 10 negative fifth. Why? Because it's smaller than 1. If you're smaller than 1, you're going to go negative. Okay. Does that come? What happened? Come on. Oh, look. Aha. So if you walk to the right, use a negative exponent. If you walk to the right, that means your number's less than 1. If you walk to the left, it means you're greater than 1. So if you're greater than 1, you're going to have a positive exponent. If you're less than 1, negative exponent. So move the right 5 places. Absolutely. Okay. How many kilometers is 2.3447 times 10 to the 7th nanometers? Uh-oh. It's one of those ones where we're mixing prefixes again.
So you're adding the zeros.
Yeah. So
Not 6 zeros.
first convert C. This is the way I do it. I don't like this, having these two things together. So I'm going to convert 2 meters and then to kilometers, right? I'm going to take the prefix off and make it the base unit, and then I'm going to add the prefix I want on. So dimensional analysis. So 2.3447 times 10 to the 7th nanometers equals 2.344 times 10 to the 7th nanometers times 10 to the minus 9th meters over 1 nanometer. So I'm going to put what I want to get rid of on the bottom so that those units cancel out and convert to the units I want, which is meters. And remember, it takes a whole bunch of small things to make a large thing and very little of a large thing to make a small thing. Right? So you could do this the other way around, right? You could say 10 to the 9th nanometers is 1 meter. You could do that too. But this way, I'm just doing the straight addition of exponents. So I'm going to do 7 plus minus 9. And now I'm going to convert back to kilometers, right? So I want kilometers on the top because that's what I'm going to, and then meters on the bottom because that's what I'm going to get rid of. And it takes a whole bunch of meters to make a kilometer, so it's 1 kilometer is 10 to the 3rd meters. And that gives us 2.3447 times 10 to the 5th kilometers. And you'll notice that the front number didn't change, right? Because I'm only changing units, so that front number better not change. And if it does, you better redo your calculations. So that's a check, right? And then the other check is kilometers is bigger than nanometers. So you want to make sure that we have less kilometers than we do nanometers. And in this case we do, because we have 10 to the minus 5th kilometers as opposed to 10 to the 7th nanometers, right? So a smaller unit shouldn't be larger than a bigger unit. If I have $10, I shouldn't have $10,000 if I convert to $10,000, right? I should have less, I should have a portion of $10,000. That's all I'm saying there. All right. So temperature. Temperature is how we measure energy, right? Motion of energy. So the movement of molecules. The faster molecules are moving around in the room, the higher the temperature. So if you're in this room and I'm giving off heat, it's going to cause the molecules in this room to move faster and the air conditioner is going to come on more quickly. Commonly used scale in the US for weather reports. Water freezes at 32 and boils at 212. This must be Fahrenheit, right? Which is a German measurement. Celsius is the universal standard temperature scale used by science, formerly called centigrade, the most commonly used scale around the world. Water freezes at 0 and boils at 100. So let me just, this is going to sound bad, but it's true, in spite of the fact that it's, whenever you do something to the least common denominator, it doesn't make it correct, it just means it's more easily understood, right? The nuance is that people who aren't on the lowest common denominator often don't use what the people at the lowest common denominator. Just as you look through life, as you're moving forward, it's something to know. So just because everybody uses something doesn't make it the best. And just because it's accepted doesn't make it the best. So Kelvin's another temperature. This is the absolute temperature scale. This one talks about motion all the way to no movement whatsoever. So if temperature is movement, the absence of temperature is the absence of movement, right? So if I stand really still, I'm not as hot as if I move. I don't know if that counts. Like, why do they call them firemen anyway? Because they're really hot, because they're moving. Ice skaters are really cold though, and they're moving. Okay. The absolute temperature scale. So if someone's really a cold person, does that mean they're not moving? I don't know. And what about Frozen? Wasn't she a princess? Okay, Kelvin, absolute temperature scale. It's really cool because now we've gotten so close to absolute zero, we've almost stopped movement. We can't quite do it all the way, but we can get really, really close. So this definition of temperature regarding the measure of kinetic energy of motion is so close. We just put another, piece of framework around the base to make it even stronger because we've slowed down motion and it's almost exactly what we predicted. Right? So another one of those cases where guys that had no way of even coming close to measuring anything moving very slowly, we've gotten down to where it's almost an accepted fact. And that's just from 1800s, right? And we're in 2022 and we've almost stopped motion completely. And it turns out that this theory was spot on.
Why does it only use positive values? Just for fun.
Can't go below absolute
Well,
zero.
because when you get to absolute zero, you've completely stopped. So any movement at all is a movement. And so it's going to be positive,
Okay.
right? So if you were to imagine everything completely stopped, you're at zero. So any movement is going to have a value, positive value, and so there is no negative value because you can't go past no movement. So if movement is zero, any movement is positive. Does that make sense?
Yeah.
Answer your question? Good. And that's exactly the way to do it, by the way, is what Brittany just did there. You just ask. Stop me, because otherwise I'll talk until tomorrow. And chemistry teachers are famous for that. Like, most of us won't stop at the appointed time, and they almost take joy in it. I don't take joy in it, I just get so excited I keep going. All right. So one of the things we do, and for those of you that have took my other class, you recognize these three thermometers, and then there's a quiz associated with it. But what do we really need to know about the three different temperatures? You just want to kind of get an idea, right? You want to get an idea the boiling point is 212, it's 100, and it's 373.15 K. So our conversion between Celsius and Kelvin is very simple. You just add 273.15 K to any temperature in Celsius to get the Kelvin equivalent. To get the Celsius equivalent of Kelvin, you just subtract 273 from any number. And then water, like, why water? Well, because it's the most ubiquitous substance on Earth, right? Everything we do is about water. So 0 degrees, 32 degrees Fahrenheit, 273 K is where water freezes. And then where does water boil? On Celsius, it boils at 100, which makes it real easy to remember. At Fahrenheit, it's 212. A lot of us remember that. And then 373.15 K for boiling. So that's really what we want to remember. These different ways up here up top of measuring from Kelvin to Fahrenheit or from Fahrenheit to Kelvin, we're going to have available to us as a tool in our conversion sheet. So while you need to be able to do that, right, they're going to be provided to you. And what's interesting about this is, given these 3 points, right, we can recreate the equation. Right? So pretty simple. You're not going to have to recreate the equation. So derived system international units, area, volume, density, units that are a combination of fundamental units. So lengths, use the appropriate prefix. Areas, length times length, or length squared, usually meter squared or centimeter squared. So anytime we did that volume calculation already, and this just reaffirms that. Volume, anytime you know a volume, you know it's cubed, right? Areas are squared, volumes are cubed. 100 centimeters cubed is 1 liter, which is also, 1,000 centimeters cubed is 1 liter, which is approximately 1 quart. 1 centimeter cubed is 1 milliliter, so 1,000 milliliters is 1 liter, that measures up. And then it's about the size of a sugar cube. 1 meter cubed is about 250 gallons. So you see a 250-gallon tank, you think, oh, that's about a meter. And small hot tub, really small hot tub. Not convenient for laboratory use if you're too big. So we don't have one in our lab. We don't get that hot tub in our lab. Because we were working on a hot tub time machine and it just didn't, couldn't get funding. Fell through after failed attempts.
I'm sure
5 years.
The movie didn't help.
No, probably not. No, they thought we'd do something stupid with it. 12-ounce soda can is about 355 milliliters. And then we used to do 750 milliliter wine bottles, but I don't remember what that conversion is. I guess it's about 24 ounces. All right, so density is one of the physical properties of matter that we use volume and mass to combine the units. And density equals mass over volume. We did that also already. And units are kilograms per meters cubed, but more commonly we use grams per centimeter cubed or grams per milliliter. And densities, again, are one of those things where density doesn't change. If I have ethanol and it weighs 1.35 grams per milliliter, and I have water that weighs 1 gram per milliliter, and I mix the two together, they're going to form layers with the heavier density on the bottom, always. And you can use that to do separations, because water and, let's say, methylene chloride at 1.33 are not going to mix, right? Because one is polar and one is not, and so you get separation there. And you can use that separation to dissolve one thing into methylene chloride that doesn't dissolve in water, and you can separate it that way. So you can always take advantage of properties, and you can do this at home with your like just anything you have laying around the house. You can test to see what it dissolves in and what it doesn't dissolve in. All right. Because you can use all these principles anywhere in the world. That's the whole point of it, right? These little laws, these little trends we can use in our everyday life. And we often do without thinking about them, and you don't get credit for that, unfortunately. You have to think about it. So extensive properties, so now we have different types of properties, right? We have physical properties, chemical properties. We're going to divide them further into extensive properties and intensive properties. Extensive properties depend on the amount of the substance. Intensive properties don't depend on the amount of substance. Can we think of any right off the top of our head without me giving you any? Of an intensive or extensive property? I would say my lectures are extensive because it doesn't matter how much material I have on the inside, I'm still going to give the whole thing.
So it would be like the measurement of time versus the measurement of a weight, right?
Measurement of time versus the measurement of the weight.
So like if your lecture, it's how long it goes, but you can't physically measure.
So that depends on that makes it extensive.
Yeah.
Right?
First, if you have like a cup of water, you can fit.
It's always a cup.
Yeah.
Right. Okay, perfect. So one trick, unit per unit Y, or ratios of units, are always intensive. So density is an intensive property.
Are you basically meaning like if you could measure it or not, then it's intensive? I don't understand by the amount.
Right, so the density of something, what is related, so grams per milliliter, no matter how much you have of it, it's still gonna be grams per milliliter, and it's still gonna be that same amount.
Okay.
But if it changes, do we have any examples of that? No, I didn't give any examples of the other. But anything where, like the mass depends on how much you have, right? So that's an extensive property. Something like solubility is an intensive property because you can dissolve a certain amount in a certain amount. An extensive property would be how fast you run. Miles per hour? No, that wouldn't be. That'd also be intensive. No, I mean, that would be extensive, right? Because how fast you run is a proportion, so it's this. Okay. Doesn't amount on the amount because you're comparing your speed, and that can vary, but if you're running 3 miles an hour, you're running 3 miles an hour, and that's intensive. Amount of substance.
But to me, I would say like how fast I'm running, I would argue that it's extensive because what if I ran for a mile, if I ran for 10 miles, like how fast I'm running would change, right?
Okay, that's right. Right? So, but now you're measuring a mile,
Okay.
right? So if you're measuring a mile, if you're gonna run that mile, now you're comparing it to something, right? It depends on the amount. How fast you're gonna run that mile, doesn't matter. You're still gonna run that mile, and it's going to, no, it's not. It's still not going to. Mass does, right? So how much you weigh is definitely gonna depend on how much of you there is. This is gonna be bad on video, I'll tell you that right now. Intensive properties don't depend on the amount of substance. So miles per hour is a relationship. So if we're just looking at miles per hour, then you are dependent on the amount, right? Your ratio. But if you're looking at how long it takes you to run a mile, the time makes it, but it's always gonna be a mile,
Okay, I see what you're saying.
right? Anyone else? Okay. The only one I can really think of is mass. That really doesn't depend on anything else. Everything else,
Light speed?
like the amount of energy you use to run a mile doesn't depend on the amount it does, right? Because how fast you run, so almost everything, right? Even though it's a ratio, how fast you run would be what? Based on how much energy you had, which would be the amount of the substance. But your actual speed doesn't depend on anything because it's a ratio of miles per hour. That's as confusing as it might be. So let's just try to remember that density is which?
Extensive?
No. Density is intensive, right? Because it's a relationship between mass and volume, and no matter what amount you have, it's always going to have the same density.
Would like color be intensive?
There you go. Right? Because no matter how much orange you have, it's orange. Nice. And then mass would be it does depend on. So our go-tos are mass for extensive and color or density or physical property, boiling point, right? It doesn't matter how much water you have, it always boils at the same point. So
Okay.
what helps other people is the opposite of what helps me. So like I can't go the other way. I understand the physical properties of the chemicals and what that means. I can't do it the other way around, but that's what you're supposed to do to help people understand the physical properties, right? I'm supposed to be able, as a good teacher, I'd be able to give you a bunch of examples that have nothing to do with chemistry to help you get the concept because you understand those concepts. I don't. I understand these concepts, right? For me, when I think of these, I don't think outside the chemical world because I don't understand. I don't understand the world outside of my chemical perspective, right? So if you come up with something, I can say, yeah, that's it, but for me to go the other way is really, really challenging, and I should step up to that challenge.
So are we gonna need to know though, like if you asked us, for instance, on the homework, you gave a couple.
Oh, let's do them.
Options of like a physical or a chemical, and one of them was like a log burning, which
Okay.
is chemical, but do I need to tell you that that's an extensive property and also a chemical change, or?
Oh,
like
would I
how-
do that? No.
Okay.
No, I wouldn't combine those. Like, yes.
Are they
you-
related though? Like, is this related to chemical and physical, or is it its own separate thing? I don't know if that's.
Yes, yes,
A burning log would be intensive because it doesn't matter how much wood there is, it's still on fire.
right, but how long it burns.
How long it burns
Right.
would be extensive.
Right. And
So
how much
even though
energy is
fire
in that burning
intensive, How
log.
long it
How
burns
hot is it
extensive.
where you're burning it? Is it outdoors where the instructor's playing like the cold air? Is it
Right,
inside
but
furnace?
whatever we know for sure is there's a chemical process taking place. That's what we're looking for in that. I'm not combining those ideas into one problem yet. And I may never at this level for those,
Okay.
right? I just want you to be able to identify them. So if I gave you a mass or a color or a density, I'd want you to be able to label those. And if you want more definitions of that, again, that's what I think the book and resources are for, or for further examples of what I give you in class. But I'm not gonna hold you to any more than this, because this is the equivalent of a freshman class at a university. Okay? So if you take this class and you pass this class with a very good grade, you would pass that class with a very good grade, as opposed to getting a good grade in here based on a class that they wouldn't offer, that when you got there, you'd be like, I don't know that. I've never been exposed to it. So exposure is also good, right? So even just being exposed to this level and getting through because you showed up is better than not being exposed to this level and getting an A. Not that any of us here do that. Okay, so some densities. We want to be able to kind of just think of things. When I think of density, I think if I pick it up and it's the same size as something else, is it heavier or lighter? So if I pick up ice, is it heavier than water? And the answer is no, right? I'd rather carry 5 pound, no, not a 5 pound bag of ice compared to 5 pound of water, but I'd rather carry an equivalent amount of water as ice, right? I'd be heavier. Oh, I don't want the water as much as I want to carry the ice. Be a little bit lighter. So, but let's look at two metals. So iron is 7.9 grams per cubic centimeter, and copper is 9, and lead is 11, and gold is 19 grams per cubic centimeter. Which one are you going to carry?
Iron.
I'm going to carry the gold. It's worth a lot more.
Oh, well, yeah.
Yeah. So I mean, the extra weight, okay, whatever.
I choose platinum.
Yeah. Well, platinum, where is
It's not on
that?
there.
Oh,
It's just worth more in general.
right. And so is what's the one that goes along with it?
Well, uranium, but you'll die.
Yeah, that won't do you any good. Palladium, maybe. All right. So the idea is that you can judge a substance by how heavy it is in the same amount. And again, you'd probably rather carry water than mercury. Okay.
So that question, what's heavier, a pound of iron or a pound of feathers?
Right. They're the same weight.
Yeah.
Yeah. You got to get up a lot earlier in the morning to fool an old guy. So a lump of metal weighs 3.27 grams. When added to a graduated cylinder partially filled with water, the volume increased by 0.40 moles. What is the likely identity of the metal? So we're going to calculate a density based on the what is that called? Displacement method, right? And real quickly, 3.27 grams over 0.40 milliliters is the density of 8.18, and that's closest to,
It's closest to iron.
Copper?
Iron.
yeah,
Iron. Round
0.2, 8.2, yeah, so it's 0.8 away from copper, and
Two.
0.2.
2.22.
So since it's neither one of those, so what can it be?
It's an alloy at that point. It's a combination.
So it can't be lead, right?
No.
So what, if it has more density than the element, can it be that element? No. So it can't be iron.
So it has to be copper.
Yeah, it has to be some copper mix. It can't be iron, because iron doesn't weigh that much. All right. Or we're just wrong.
Yeah.
So, all right, that's where we stop today. Oh, we have one slide left. So density of Saturn is 0.687 grams per centimeter cubed, which means it would float on our ocean, right? You just drop Saturn right onto our ocean. It's a little big, it's a little unwieldy, and that's it. All right, thank you, and we'll see you